think. So now I was talking a bit about Dirac and using wedding quantum mechanics and relativity, special relativity. So here's another course, also by Greiner, called Relativistic Quantum Mechanics on wave equations. So this is full of Dirac stuff. The Dirac equation is features heavily in this text. And then once you have a good knowledge of Dirac's equation and special relativity and quantum mechanics and how to wed the two, you can then apply it to the interaction between particles and the electromagnetic field, and that specialty is called QED, quantum electrodynamics. Okay, and the big name for that, well, four of them, but the best known is Feynman, Dick Feynman. I haven't met him, but I wrote to him once, which was a fresher, I think. He actually wrote back, so oh, I have no idea of your ability, so I can't really comment or something. But he actually wrote back, which surprised me. All right, now two more. So I'll do 5 of his texts, five courses, graduate level courses based on his stuff. Now this is, I think, gauge theory. Yeah, this is probably an M2 second year master's level course on the gauge theory of weak interactions. You probably know there are 4 types of forces in the universe. There's the very weak gravitational force. There's the weak force, as it's called, or the weak nuclear force, like beta decay and so forth. And so that's the theory of the weak interaction. Uses ideas from QED, quantum electrodynamics, and then on a similar line, again, they're all Greiner, right? This one's on the other force. Well, then there's the electromagnetic force, and the strongest one of all is strong force, or strong nuclear force, which is the force that binds the quarks together to form protons and neutrons. So you have gluons flying back and forth between the quarks, bonding the quarks in the same kind of way analogous to electrons in atoms bind the atoms together. Well, strictly speaking, using photons, but that's QED. So this is the theory, quantum theory of the strong force. So quantum chromodynamics. So QCD rather than QED, and chromo is something to do with color. What's color? Well, it's a sort of a charge, and quarks have color. So quarks have the ordinary electronic charge, plus and minus, like electrons and positrons. But they have that kind of charge. But they also have another kind of charge called color. Now it's just a label. You could call it anything. And they have 3 charges colored. 3 color charges: red, green, and blue. Or you could, I mean, again, it's just a label. You could call it alpha, beta, and gamma, or X, Y, Z, or blim, blam, blom, whatever. But the quantum mechanics of the interaction of color, this type of charge, its dynamics is called chromodynamics, quantum chromodynamics. So when you get up to this stage, you're, well, I'd say that's M2 PhD 1 level, right? So so you can see I love Greiner. All right, so it's a long session. Now to do the second half of, well, the second square, you can do it fairly quickly. So we know about 2x2 permission matrices that are the representation of angular momentum vectors like L squared and LZ. The previous session we found the eigenvalue spectrum. In other words, all possible eigenvalues for the LZ and the L squared. So we know the eigenvalues, we've got the operator, we've got the matrix form of the operator, the matrix representation of the operator, just a 2 by 2 matrix. What we haven't done yet in the general context of eigenequations are the eigenfunctions, right? So, I mean, you know the standard format for an eigenequation. It's operator, eigenfunction, that's the left-hand side, equals eigenvalue, eigenfunction. Yeah? So what are, for these 2 by 2 matrices, what are the eigenfunctions? Right? So that's for spin. So what are the spin eigenfunctions or eigenvectors? Vector function, effectively the same, right? So now let's try to find what these. Well, in this context, they tend to be called eigenvectors, just a convention. But eigenfunctions, same thing. So what are they in the context when you're talking about spin angular momentum? So now before we actually start solving what these eigenvectors, eigenfunctions are, we need a little notation. We're going to change the notation a little bit, right? Firstly, now you've seen these before in an earlier session. They as matrix representations of the spin, spin operators. So like L squared and LZ. Okay? But here they're stripped of the I H bar. It's just the matrix part. These three matrices together are simply called the Pauli spin matrices. Okay? So and the matrices are labelled by sigma. Okay? And three of them. So sigma x is this matrix, sigma y is that one with complex values, and sigma z is this. Now these are the eigenvalues for when you measure the orientation of your angular momentum relative to the x-axis. So these three are the Pauli spin matrices. Okay, so you need to memorize that, and these will pop up all the time from now on. They're very, very important. All right. Now here's the notation change. We're now in the context of spin. We're going to be talking about spin for quite a while. So instead of using the letter L for angular momentum, we're now talking about a particular kind, a kind of intrinsic angular momentum, like spinning on its own axis, speaking by analogy. So we're talking about spin. So we're going to start from now on using the letter S for spin, instead of L. Okay? So we're now talking spin angular momentum, S. So we'll have operators S squared and SZ, analogous to, or comparable to what we had before with L squared and LZ. Okay? Because now we're talking about spin, and we're assuming these matrices 2 by 2, they obey the same kind of commutation relations as the operators, right? These Hermitian operators. And now we have Hermitian matrices, right? Spin matrices. We'll use the Pauli spin matrices, right? So we're switching from L to S, okay? That's change of notation. All right? Well, now we can start doing a bit of math. What are the eigenfunctions for 2 by 2 spin matrices, for the Pauli matrices? Well, your 2 by 2 matrix is a kind of operator, right? It's a matrix that operates on something and changes it into something else. Well, so typically an operator operates or changes a function into some other function. So if your matrix operator is a 2 by 2 matrix, what could that operate on? I mean, in mathematical terms, what could it be? Well, I guess the simple answer is just a column vector, right? A 2 by 1 column vector. 2 rows, one column of this form. Okay, so that's what your eigenfunctions will look like. They'll just be a column vector. Or the ket will be. The bra will be a row vector, right? 1 row, 2 column. So horizontal, you have two elements in a row, in a line. So that'd be the bra, and the ket would be a vertical, 2 numbers vertically, a column vector. Okay. So here we're talking column vector. So that's your eigenvector, or eigenfunction, eigenstate, whatever. All right. So here is that is your S of z. S of z now. We're not talking L of z anymore. Forget about L's. We're talking S's from now on. Okay. So S of z, eigenstate. Here's your operator again. So you're just substituting for S of z this, right? Times your 2 eigenfunctions, eigenvectors, and so eigenvalue. So mu. We don't know what mu is yet. Well, actually, we do know, but we can substitute that in later. So we're writing out one eigenequation for S of z, and writing out another eigenequation for S squared. Right? And since these two commute, we're assuming the spin type angular momentum obeys the same commutation relations as does orbital angular momentum. Right? So that means Sz, or Sz, and S squared, they commute. And because they commute, therefore they have the same set of eigenfunctions, eigenvectors. Okay? So in other words, the eigenfunction here, here will be the same as here, here. These 2 operators share, or they have the same set of eigenfunctions. Okay? So AB, AB. And it's just a column vector. Right? Now the S squared operator is from earlier sessions. It's 3 h bar squared over 4. His times this matrix here, which is it's not one of the Pauli spin matrices. Okay, all right. Well, now you can solve this, right? You can solve for what A and B are, and we'll do that in the next session. And you'll get, in fact, well, I'll wait for the next session. So rather a long-winded session, but I hope you found it interesting. And as usual, a bit of a plug for future courses and a certain amount of fun.